Hello guys, welcome back to my channel Gamma Di Gamma. So in the previous video we did a legendary contour integral, and in this video we are going to apply that same result to another weird integral. So let's get started. Okay, so here is the subject of today's video: integral from 0 to infinity hyperbolic cosine of x multiplied with hyperbolic cosine of ax divided by hyperbolic cosine of nx dx. Okay, instead of saying hyperbolic cosine, I'm going to call this cosh, and as is the convention on this channel, I'm going to call this prime integral I. So what I can do is, first of all, split the hyperbolic cosines into exponentials, because we know cosh of x is going to equal e to the x plus e to the negative x divided by 2. So I can do that. On top we have 1/2 and 1/2 because of this, and we're dividing by 1/2, so ultimately we have 1/2. Integral from 0 to infinity, we have e to the x plus e to the negative x, e to the ax plus e to the negative ax. We're all going to divide this by e to the nx plus e to the negative nx dx. Okay, now one natural thing that we can do, because exponentials have this nice property that their derivative or indefinite integral, which you also know as the antiderivative, is itself. So we can make the substitution, let t equal to e to the x, because dt will always be e to the x dx. Using this, we have 1/2 integral. Now when you substitute 0 in place of x, you have e to the 0, which is 1, and e to the infinity diverges to infinity. What you can do is have this written as t plus 1 over t, because that's the negative. E to the negative x is 1 over t if you compare exponents. We have t to the a plus 1 over t to the a divided by t to the n plus 1 over t to the n, and dx was just dt over t. So it turns out we can get rid of the things in the denominator, basically the t's that are in the denominator in each time. So we have 1 plus t squared, 1 plus t to the 2a. I'm basically doing cross multiplication here. 1 plus t to the 2n, and all these other denominators. So we have an n in the denominator of the denominator, so it'll become positive, and this a that was on top will be a negative, and this 1 because of this will be a negative, but we also have this t, so that will become a 2 dt. All this is just substitution and basic algebra. If you are confused at this point, please pause the video and just do it on a piece of paper. Okay, now the issue with this I is that it's going from 1 to infinity. That's a little concerning, because the natural way of looking at things was from going from 0 to infinity. So can we exploit some sort of symmetry? And if you're confused, symmetry, how, why? Infinity isn't even like a proper interval of integration. So how are we going to do that? So see you on a fresh page where I'm going to explore this option. Okay, so previously we had this, and now I would urge you to consider this integral j, which is essentially, just forget the 1/2, the same integrand, except it's going from 0 to infinity this time. So 1 plus t squared, 1 plus t to the 2a divided by 1 plus t to the 2n, and we have t to the n minus a minus 2 dt. Okay, now what I can do is split this interval, so I can have one integral going from 0 to 1, same integrand obviously. I'm just exploiting the linearity of the integral and splitting it up, the interval from 0 to infinity as 0 to 1 and 1 to infinity. You can even justify this using limits, but I thought this was sort of a given. And then we have integral from 1 to infinity, which is precisely the I we had. Actually 2 times I in this case, because we didn't take the 1/2 factor. Integral from 1 to infinity of this integrand is 2 times I. I'm just directly writing that. I hope you see that. Okay, now what I'm going to do is I'm going to let t equal 1 over w. So t dt is negative 1 over w squared dw, and I'm going to substitute in this integral. So j is precisely integral from 0 to 1 of well, actually if you substitute these guys in, you're going to have 1 over 0, which tends to infinity in the limit, infinity to 1 with this substitution. And you have 1 plus 1 over w squared, 1 plus 1 over w to the 2a, all divided by 1 plus 1 over w to the 2n, 1 over w raised to n minus a minus 2. And we have a negative 1 over w whole thing squared dw. That's this factor. So notice this 2 cancels with this. The negative can be used to split the order. I forgot my 2i. I can flip the order of integration 1 to infinity now. I can do some, LCM magic over here. W squared plus 1, w to the 2a plus 1 divided by w to the 2n plus 1, and here we have w to the n minus a minus 2, because again I did the same LCM that we had for I. Let's not forget the dw. And look at this. This is precisely 2 times I again. You can just change the w to t again. It doesn't matter because it's a variable of integration, of definite integration. So j just becomes 4 times I, which means that I should be 1/4 of j. So we can write I as 1/4 of j, and j was integral from 0 to infinity 1 plus t squared 1 plus t to the 2a over 1 plus t to the 2n, and with this annoying stray factor of t raised to n minus a minus 2 dt. That is essentially what integral I is. And now this is way easier to work with, because now we can completely use the result from the previous video, and we can explore this in more depth on a further page. So see you there. Okay, so this is precisely what I turned out to be. Now I would like to expand everything, especially the factors in the numerator. So on expansion I have 1 plus t to the 2a plus t squared plus t raised to 2a plus 2 divided by 1 plus t to the 2n dt. Now I would like to multiply this numerator by this factor that was always on top, this stray factor that we called. And when I do that, I have t raised to n minus a minus 2 plus t raised to n plus a minus 2, if I'm doing this right, t raised to n minus a plus t raised to n plus a divided by a common denominator 1 plus t raised to 2n dt. I would like to split each of these guys into individual integrals y, and this is y. Remember this result from last time, integral from 0 to infinity of t raised to a minus 1 over 1 plus t raised to 2n dt is precisely pi over 2n times the cosecant of pi a over 2n. I did this with the legendary contour integration method, and notice the denominators are the same, so we can split these into this guy, this entire I, into 4 integrals of this type, of this start type over here. And when I do that, all I have to do is, well, the pi over 2n factor is common for each of them because they have the same denominator, and then just change the cosecant term for every changing power. So for a minus 1 we had pi over 2n multiplied with, this power, the power of t in the numerator plus 1. So just add 1 for this guy, which means cosecant of pi over 2n times n minus a minus 1. I just added 1 plus then this guy, cosecant of pi over 2n times n plus a minus 1 plus cosecant of pi over 2n n minus a plus 1 plus cosecant of pi over 2n n plus a plus 1. Okay, so we have pi over 8n over here. Well, if you just expand this argument of the cosecant, we have pi over 2 minus pi over 2 times some stuff. So we have pi over 2 minus pi over 2n times a plus 1. You can call this an arbitrary angle. Well, take the negative outside if you want. Call this an arbitrary angle. So we know that the cosecant of pi over 2 minus some angle is just the secant of that angle, pi over 2n a plus 1. And the best part is, assuming we had like a negative angle here, like a negative a, negative 1, we can write it as, positives. We can just write it as a plus 1. If we had negative a, negative 1 inside a secant, we can directly write that as secant of a plus 1, because the secant is an even function, just like the cosine. It's essentially the reciprocal of the multiplicative reciprocal of the cosine. So you can see that, and so we can use this over here. So we have, this is the complementary angle property that we're going to use. We have secant of the angle apart from the n, so pi over 2n, and the negative was taken out, so a plus 1 plus secant of pi over 2n. Here we can have here we'll actually have negative a plus 1, but since the secant is even, we can directly write that as a minus 1 as well, plus secant of pi over 2n, and again we can use the evenness of the secant, plus secant of pi over 2n a plus 1, again using evenness. And the best thing about the evenness of the secant was that, notice this is just the same as this, and that this is the same as this. So we just group some terms. We can take a 2 common for all these guys. So we have secant, just write one of each, pi over 2n a plus 1 plus secant of pi over 2n a minus 1. If you want, you can simplify. Pi over 4n times the secant of pi over 2n a plus 1 plus the secant of pi over 2n a minus 1, and then we're done. That's it. Yeah, that's it. All thanks to this nice result that I derived in the last video. So please check that video out. It's an epic one. I think the first one on YouTube until now. So please check it out. It's, you see how powerful this result is. I mean, it just decomposed an integral of, I call it the hyperbolic cosine trifecta, the cos trifecta. There practically seemed no way to do this, right? I mean, this was as scary as it gets. I mean, I at first thought whether this converges or not. I was doubting that. But look how nice everything turned out. But the best thing is, using a similar approach as this, we can even find that the sinh trifecta, the hyperbolic sine trifecta, a similar thing if we want to do with the sinh function, does not give such a nice answer. It gives 0. That's because in this symmetry part, both halves, so this guy from 0 to 1 is just the negative of the other half, which is going from 1 to infinity basically, and you can check that using using substitution. So how the question we had about symmetry before, you see how valid that is now, because it completely destroyed one integral, the hyperbolic sine, the sinh function, because it's odd if you want to think about it that way. But it's not exactly an odd, it's not exactly a positive negative kind of symmetry. It's a reciprocal symmetry. It's a multiplicative reciprocal symmetry. Because what's happening is, you take this substitution, which is basically the multiplicative reciprocal substitution, instead of the classical upper bound plus lower bound. So if we had integral from a to b, instead of having b plus a minus x, instead of substituting that for x, we're using this kind of, because it's an improper integral, and this is what works. You can't use this. I mean, how do you add and subtract infinity? It doesn't make sense. So this is actually an important technique, and it can help you in many questions where you can't, where most standard techniques fail and stuff like that. So I hope you enjoyed this video, guys. So if you like this video, please like and subscribe to my channel, recommend me to your friends in the math community, share the video around, just make me big. And in the meantime, stay home, stay safe, keep doing math, and peace out. Stay tuned for more content.